Hello everyone, my name is Bart and today we are going to walk you through our work on message passing based inference in the gamma mixture model, which we wrote together with Ismail, Albert, Dimitri and Professor De Vries from the BIASlab research group at the Eindhoven University of Technology.
Hey guys, I've got an interesting problem to solve. I have a data set that to my knowledge should be coming from some sort of mixture distribution. I'm aiming at using a Gaussian mixture model. What do you guys think about it?
A Gaussian mixture model seems to be a nice choice, but we can see that the data has positive support and seems somewhat skewed. Perhaps we can use a gamma mixture model instead. But how should we implement this and how should we infer the parameters of this model?
I have an idea, guys. What if we use Forney-style factor graphs for modeling gamma mixture and also to run Bayesian inference for it?
Why would we want to do that?
Factor graphs are a nice choice to represent factorized probabilistic distributions and also conditional independencies in your model. It also allows for an efficient Bayesian inference with message passing. We can efficiently propagate summaries of parts of our model through our graph for performing inference. So in Bayesian setting, to obtain a posterior of some model variable, you usually need to marginalize your generative model's overall remaining variables. It involves computing big integrals, but factor graphs allow you to reduce your problem complexity from exponential to linear by computing these subintegrals. And these subintegrals propagate summaries as messages on the graph.
Oh, that's exactly what we need. How can we represent gamma mixture model in the factor graph?
So if I understood Dimitri correctly, we can do that as follows. Let's say that we have our observations X being generated from some gamma mixture process with different parameters for each of the mixture components. Then we can say that each observation has to be generated from each mixture component, but one mixture might be more probable than another. Let's try to capture this uncertainty in this categorical random variable S. If we then also combine this with a global Dirichlet prior over these categorical distributions, we can figure out what the corresponding mixture coefficients are.
Another nice property of a factor graph is that you can decompose and reuse different complex distributions in your model in the form of a composite factor node.
And what is exactly inside this composite node?
For example, you can represent it as a collection of gamma nodes connected to a selection variable with a multiplexer node.
Okay, and how do we run inference on that?
That's a good question. I tried solving the integrals for these exact messages as Dimitri showed previously, but I didn't manage to find an easy closed form solution. How can we then still perform inference in this model?
What if we perform approximate Bayesian inference with variational message passing? It optimizes free energy functional, and we can also verify if our method converges. But there's a problem. The gamma node does not have a closed form solution for the normalization constant of the variational messages towards the shape parameter alpha. It would be difficult to compute a closed form solution for the normalization constant of the posterior marginal over the shape parameter.
I have an idea. How about we use expectation maximization algorithm and approximate our posterior with just a single value? It turns out that there is a unique solution for this optimization problem. Guys, I've just tried this method for two setups. At first, I assumed that mixing coefficient is unknown, while I kept parameter priors for the parameters of gamma distribution informed. In this case, we can easily recover mixing coefficient within just 250 EM iterations. At second, I made the prior for mixing informative and I tried to compute the values of shape and rate parameters of mixtures. The method finds the values correctly. However, it takes more time for the algorithm to converge.
In the meantime, we come up with another solution. We can try to approximate the moments of this resulting distribution and obtain the Bayesian posterior from these. By performing importance sampling, we can perform the integrations for calculating the moments numerically. This will then converge to the true mean and variance values. Unfortunately, it will also be slower.
Great results, guys. It looks like this model might be useful in where we need to model some data with positive support. We should definitely add this gamma mixture node to our package reactivemp.jl, so it can be used as a plugin node in any graphical model. I just tried to implement it there, and creating the model and running Inference is really straightforward.
Okay, let's summarize what we've done. We introduced the gamma mixture node, we validated and verified the approach on different data sets. We also added this gamma mixture node to reactive message passing so that it can be reused in any graphical model. When comparing EM to moment matching, we noticed that the expectation maximization has a faster evaluation time, but unfortunately doesn't yield full posterior. In contrast, moment matching retain uncertainty, but it is slower in terms of computation time.
Thanks a lot for your attention. Please have a look at our full paper for more information, and also don't forget to check out our reactivemp.jl package for automated Bayesian inference.